In section 2.6, we take a deeper look at how electrons are organized in atoms. So, just recalling that electrons reside outside of the nucleus. They're at a great distance from the nucleus, orbiting around the nucleus like planets around the sun. It's important to recognize that higher energy electrons are found at greater distance from the nucleus than lower energy electrons. That is, the further away from the nucleus the electron is, the more energy it has. The model that we're going to use to describe where electrons are located in atoms was developed by a guy called Erwin Schrödinger. And he developed something called the Schrödinger equation, that if you solve it, it tells you where an electron is and how much energy it has. Now, this model is a quantum mechanical model. You might have heard of Schrödinger in terms of Schrödinger's cat. And Schrödinger's cat is kind of trapped in two states at once, which this little comic over here is trying to explain. So it's kind of fun to talk about Schrödinger's cat just by, for a reason of historical completeness. So Schrödinger's cat was a thought experiment to illustrate that sometimes when we're talking about statistics, what we come up with doesn't make a lot of logical sense. And the quantum mechanical model of an atom is a statistical model. So in the Schrödinger's cat thought experiment, what you have is a crate that is divided into two sections. And the divider has air holes in it, so air can get across the barrier. And on one side of the barrier, you have a cat. On the other side of the barrier, you have a fairly elaborate setup that might poison the cat. And what we have is a sample of a radioactive material that if it undergoes radioactive decay, it will activate a Geiger counter. If the Geiger counter is activated, then a hammer drops and smashes a vial that contains a poison that is released as a vapor, and the cat dies. Now, the radioactive material is chosen such that it releases a particle that will activate the Geiger counter on average about one every hour. So if we seal this whole thing up and put a lid on the box, we can't see what's inside, and we wait for 30 minutes, well then there's about a 50-50 chance that the Geiger counter went off, that the hammer dropped, and the cat died. So if there's a 50-50 chance that the Geiger counter really did go off, there's a 50-50 chance that the cat is dead. So the best way of describing the cat statistically is to say that it is half dead and half alive. And this was just a little fun experiment by Schrödinger to illustrate the point of don't take statistics too seriously. Of course, there's no such thing as a half dead and half alive cat. It's just the best way that we have of describing the cat if we can't see in the box. So Schrödinger's equation, when we solve it for where the energy of the electrons in atoms, gives answers which are what we call quantized. So the energy of electrons in an atom is quantized. That means that it can only have certain specific values. It can't have any value. So this is kind of like when you're walking upstairs, you can only be stable at certain heights when both feet are on the stairs. However, when you're walking up a ramp, you can be stable at any height you choose because we have what we call a continuum of states. So quantized states means that you can only have certain values. A continuum of states means you can have any value, and the energy of an electron in an atom is quantized, which means that not all values for its energy are possible. So in the quantum mechanical model of the atom developed by Schrödinger, the space where electrons are located is divided into three regions. We have shells, subshells, and orbitals. And each of these is a more precise description of where the electron is than the next. It's kind of like how a postal address works. The state is a pretty big description of where somebody would be located. The city narrows it down a little bit more, and then the street narrows it down quite finely. So the same is happening with shells, subshells, and orbitals. This is the big picture view. This is zoomed in a little more, and then this is the best that we can do. So electron shells correspond to layers of electrons. Electrons in the same electron shell spend most of their time at a similar distance from the nucleus. So the first shell, nice and close to the nucleus, this is the lowest energy electrons. The second shell, the layer that is further out, these have higher energy. And the third shell, even further out still. Often, people will designate the electron shell with the letter N. So in this particular atom, we would have N equals 1, or N could equal 2, or N could equal 3, because there are 1, 2, 3 layers of electrons. It's kind of obvious, right? Now, you can see that these shells get bigger. So that means that every shell that we move out can accommodate more electrons. And the little formula that you want to remember is that the maximum number of electrons in a given shell is 2 multiplied by n squared. So for the first shell, we can have 2 times 1 squared, or 2 electrons as the maximum number of electrons in the shell. For the second shell, it would be 2 times 2 squared, or 8 electrons that could fit in that shell. For the third shell, it would be 2 times 3 squared, which would be 18 electrons. So here we have all the way out to 7 shells, which is the largest number of shells for any known atom. So you can see the shells get bigger, and the number of electrons that they can contain increases quite a lot. Now, within shells, there are regions of space called subshells. So going to the next layer of detail. Electrons within a subshell, within the same subshell, have the same energy. There are 4 types of subshells: S, P, D, and F. And that is in order of increasing size. S subshells are the smallest and can contain 2 electrons. P subshells are bigger and can contain 6 electrons. D subshells can contain 10 electrons, and the largest subshell is the F subshell, and that can hold 14 electrons. Within a subshell, electrons are found within regions of space called orbitals. So this is our final level of detail that we're going to be able to go to as far as where the electron is located. What an orbital describes is the region of space within a given subshell where the electron is most likely to be found. The maximum number of electrons in any orbital is 2. What this means is S subshells have only 1 orbital because they can contain a maximum of 2 electrons. P subshells are made up of 3 orbitals because they can contain a maximum of 6 electrons. D subshells must have 5 orbitals because they can contain a maximum of 10 electrons. And F subshells must have 7 orbitals as they can contain a maximum of 14 electrons. So it kind of looks like this. The first shell has only 1 subshell. The second shell has 2 subshells. The third shell has 3 subshells, and any shell 4 or higher has 4 subshells. In shell 1, we have what we call the 1s subshell. The 1 indicates the shell number, and the S indicates the type of subshell. In shell 2, where we have 2 subshells, we have the 2s and the 2p. The S subshell is made of 1 orbital, but a P subshell is made of 3. Often orbitals are indicated using lines. The third shell contains 3 subshells, the 3s, the 3p, and the 3d. And recall that the D subshell is made of 5 orbitals. From the 4th shell onwards, we have 4 subshells. So for example, for the 4th shell, we would have 4s, 4p, 4d, and 4f. 1 orbital in the 4s subshell, 3 orbitals in the 4p, 5 orbitals in the 4d, and 7 orbitals in the 4f. It's important to realize that shells that sit closer to the nucleus are lower in energy than shells, are lower in energy than shells that are further away. So orbitals have characteristic sizes that depend on the shell number and the subshell type. So s orbitals are spherical in shape, and they increase in size as the shell number increases. So an electron that's in a 1s subshell will be found somewhere on the surface of this sphere, and an electron that's in the 3s subshell will be found somewhere on the surface of a sphere centered at the atom that's much larger. P orbitals have 2 teardrop-shaped lobes, and it's important to recognize that a p subshell is made up of 3 p orbitals. These p orbitals are at 90 degrees to each other and are aligned along the x, y, and z axes. So sometimes they're labeled px, py, and pz for this reason. Now, D and F orbitals have complicated shapes with multiple lobes. D orbitals tend to have this clover leaf type shape with the 4 lobes on there, and you want to remember that there are 5 d orbitals in a d subshell. F orbitals often have very complicated shapes. This one here has 8 lobes directed towards the corners of the cube, and you want to remember that there are 7 f orbitals in an F subshell. So one of the important things that we're going to learn how to do is to write what we call the electron configuration. And an electron configuration is a description of how many electrons an atom has in each of its subshells. In an electron configuration, what we will do is we'll list out each of the subshells from lowest to highest energy, and then following each subshell we'll use a superscript to indicate how many electrons are contained in that subshell. So an example of this would be if we were asked to describe an atom that has 2 electrons in a 1s subshell, another 2 electrons in a 2s subshell, and then finally 4 electrons in a 2p subshell, we would write this: 1s2, and you can see the 2 is a subscript indicating that we have 2 electrons in that subshell, followed by 2s2 again, because there are 2 electrons in that 2s subshell, and then finally 2p4, because the 2p subshell has 4 electrons in it. So this atom in total would have 8 electrons. So when we build up the electron configuration of a multi-electron atom, we're going to use what we call the Aufbau or building up principle. This was determined by a guy called Niels Bohr, who you might have seen in the Oppenheimer movie, but he was a much older man in that movie than what we see in this photo here. It's a little bit weird because Aufbau is a German word, but Niels Bohr was Danish. And my theory is that he was probably trying to impress Albert Einstein, who was one of the world's most famous physicists at the time of he was doing this work, who was German. Okay, so if we're going to list out all of the subshells in order of increasing energy, we see that it follows a really complicated pattern, and it's going to be difficult to remember this order. So what we're going to do instead is we're going to use this thing called an Aufbau diagram that makes the order of filling the subshells much easier to remember. So in the Aufbau diagram, in the first column, we write 1s through 7s. Then in the second column, starting at row 2, we write 2p through down to 7p. In the third column, we write 3d down to 7d. This diagram cuts it off at the 6d, but you can write all the way down to 7d. And then in the fourth column, starting at the fourth row, we write 4f all the way down to 7f. And again, this diagram cuts it off at the 5f. You don't need to if you don't want to. Then we draw in these diagonal arrows, and we've completed the Aufbau diagram. So how we write an electron configuration is we just move down these arrows in a zigzag fashion, filling up each of the subshells. Now, it's important to recognize that you need to be able to draw the Aufbau diagram. It's not something that we give you on tests and quizzes. So you will want to practice drawing the Aufbau diagram. So in addition to knowing the Aufbau diagram, you also will need to know the maximum number of electrons in each type of subshell. So for an S, that is 2 electrons. For a P, that is 6 electrons. For a D, that is 10 electrons. And for an F, that is 14 electrons. And then to use the Aufbau diagram, we just keep moving along our arrows until we have obtained the correct number of electrons. So if I had an atom that had 14 electrons, I would start with 1s, and I would put 2 electrons in, and then I would move on to 2s, where I would put another 2 electrons. Then I would move on to 2p, where I would put 6 electrons, and then I would move on to 3s, where I would put 2 electrons, and then over to 3p, and I would put another 2 electrons, and that would get me up to my 14. So it's a pretty simple kind of procedure. Okay, we'll go through that now. So we're going to work through the electron configuration for the first 2 elements, hydrogen and helium. Now hydrogen has atomic number 1, which means it has 1 electron. So its electron configuration will just be 1s1. Helium has atomic number equal to 2, which means it has 2 electrons. So that's going to finish off the 1s subshell. So now as I move on to my next atom, I have to start my next row. So lithium has atomic number 3, so it's got 3 electrons. We're going to go 1s2, 2s1. Beryllium, according to the periodic table, has 4 electrons, so we're going to go 1s2, 2s2. So now when we start our next atom, we're going to start at the 2p. So boron has 5 electrons. So we're going to go 1s2, 2s2, 2p1. And now it gets kind of boring because the 2p subshell can take up to 6 electrons. So carbon with 6 electrons is going to be 1s2, 2s2, 2p2. Nitrogen with 7 will be 1s2, 2s2, 2p3. Oxygen with 8 will be 1s2, 2s2, 2p4. Fluorine with 9 will be 1s2, 2s2, 2p5. And then neon with 10 will be 1s2, 2s2, 2p6. So now we've finished the 2p and we're going to move on to the 3s. So the 3s subshell can hold 2 electrons. So sodium with 11 electrons will have electron configuration 1s2, 2s2, 2p6, 3s1. And then magnesium with 12 electrons has 1s2, 2s2, 2p6, 3s2. So at this point we're full and we've got to move on to the next subshell, which is the 3p. So again, it's going to get boring as we move from aluminum all the way down to argon. We're steadily filling up the 3p. So at this point, you're probably noticing that a lot of this is getting repeated every time, isn't it? All right. And it sure would be nice if we could find a shortcut so we didn't have to keep writing the same stuff out again and again and again. So thinking about that, we should recognize that it is the outer electrons, those that are in the highest shell, that give an atom its chemical properties, because when two atoms come together, they're going to interact with one another by their outermost electrons. The core electrons that are in the filled up inner shells don't contribute very much to an atom's chemical property because, well, those electrons don't really interact with the electrons on other atoms. So what we can do is we can write what's called the abbreviated electron configuration that focuses our attention on those chemically important outer electrons. And it's not that difficult a process to do. So if we look at the electron configurations of calcium and potassium, well, we can see that the electron configuration for the first 18 electrons is exactly the same. This electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, is the electron configuration for the noble gas argon. Okay, argon. Now, the electrons that are interesting chemically are these ones that are in the outermost shell. So all of the inner shells are completely filled, right? So the fact that the electron configuration for the inner shells that are completely full up is the same as that for argon is kind of the key to figuring out how we might abbreviate this electron configuration to focus on those chemically important 4s electrons. So all we're going to do is, instead of writing out the electron configuration for those first 18 electrons, we're going to just substitute the symbol for argon in parentheses to represent them, because those electrons are equivalent to the electron configuration for argon. And what this does is two things. It makes it a lot easier to write out the electron configuration, but it also focuses our attention on those chemically important 4s outer electrons. So the general rule that we're going to use to write the condensed or abbreviated electron configuration of an element is we're going to write the symbol for the previous noble gas in parentheses, and then just write the electron configuration for the electrons that are needed to finish off the the electron configuration of the atom. So here's sodium. It has a total of 11 electrons. The first 10 are the same as those found in the preceding noble gas, neon. So instead of writing out 1s2, 2s2, 2p6, we're just going to write out the symbol for neon in square brackets. Similarly for magnesium, we want to focus on the outermost electrons, and we recognize that the electron configuration for the first 10 is just the same as those for the preceding noble gas, neon. And so instead of writing out those electrons in their full configuration, we're just going to write out the symbol for neon in square brackets and then complete the electron configuration by adding 3s2. For boron, where we have 5 electrons, the preceding noble gas is helium. So instead of writing out 1s2, we're just going to write out the symbol for helium in square brackets and then complete the electron configuration with the outermost electrons. Okay, so it's pretty easy to move between the complete electron configuration and the condensed electron configuration. We just got to identify the previous noble gas and then identify the outermost electrons. So let's look at an exercise from the book. It's always good to practice the exercises that are given in the chapter, just for preparation for our quizzes. So let's have a look at this. It says, using figure 2.6.2 as your guide, which is an Aufbau diagram, write the electron configuration of a neutral chlorine atom. The atomic number of chlorine is 17. So the first thing we want to do, step 1, determine the number of electrons. That's going to be 17 because the atomic number for chlorine is 17. And then now we have to just fill up the electron configuration, remembering that we get 2 electrons in an S subshell, 6 electrons in a P, 10 electrons in a D, and 14 electrons in an F. So first of all, we're going to fill up the 1s. So that takes 2 electrons. Now that's done. Then we move on to the 2s, and that takes another 2 electrons. So that's done. And then now we're on the 2p. That takes 6 electrons. So that's 4. Then we move on to the 3s. That takes 2 electrons, and that's 4. And then we have to loop around and start the 3p. And we only want to go up to 17, and we're already at 12. So that's going to take 5, and it'll have 1 empty spot in there. So the electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p5. And it doesn't ask for the abbreviated electron configuration, so I'm just going to leave it be. It says the electron configuration of neutral calcium atom is, write the abbreviated notation. So the first thing that we want to do is identify the outer electrons, okay? And then, so that's going to be these guys. And then count up the number of electrons in here. So we've got 10, and then another 6, 18 electrons. And the noble gas that has 18 electrons is argon. We can find that on the periodic table. And so our abbreviated electron configuration will be argon 4s2. Okay, so what we're doing to find the preceding noble gas is we're looking in group 8A, and then we're looking here at the atomic number to see how many electrons each of those noble gases have. Okay. So when we look at the periodic table, there's some interesting things to see. We have the representative elements, which are like the A groups. And then we have these transition elements, which are what we call the B groups. We're mostly going to be concerned about the arrangement of electrons in elements that are in the representative elements. There's kind of like, if you look at a periodic table, 1, 2, 3, 4 blocks, and the first block is 2 columns wide. The second block in where the B groups are is 10 columns wide, and the block over on the far right hand side is 1, 2, 3, 4, 5, 6 columns wide, and then this block at the bottom here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 columns wide. So we've got 2 columns wide, 6 columns wide, 10 columns wide, 14 columns wide. 2, 6, 10, 14. Hey, I think we've seen those numbers before. So let's look at some elements here that are in group 1A. Group 1A, okay? And if we look at the electron configurations for all of these elements that are in the same group, we observe an interesting trend. All of the elements in group 1A have an electron configuration where the outermost shell corresponds to the row of the periodic table where you find the element. So lithium is found in row 2 on the periodic table, sodium is found in row 3 of the periodic table, potassium row 4. So when you've got your electron configuration and you want to check to see if you got it correct, have a look and see whether your element is in the row corresponding to the outermost shell. That's a great way of double checking. But something else we want to really think about here is what this means is every time we move down a row in the periodic table, we're going to be adding a layer of electrons. So that's what the rows in the periodic table correspond to. Every time we move down one, we add a layer of electrons, which is kind of cool. Okay, you'll also notice that all of these elements that are in group 1A have an electron configuration that ends with 1 electron in an S subshell. So they always end with a singly occupied S subshell, which is interesting. 1 electron in group 1. Okay. Let's go over to group 5A and have a look at the electron configurations of some of these elements. Okay. So nitrogen, which is in row 2, has for its highest shell, shell number 2. Phosphorus, which is in row 3 of the periodic table, has for its highest shell, shell number 3. Arsenic, which is in row number 4 of the periodic table, has, you guessed it, 4 shells. Antimony, which is in row 5 of the periodic table, again, you guessed it, has 5 shells. Now, remember that these guys were in group 5A. And if we start looking at the total number of electrons in the outermost shell, we see that in every case, it adds up to 5. And it turns out that the group number for the A group elements is always equal to the number of electrons in the outermost shell. So if I went to group 6A, I would expect all of those guys to have 6 electrons in outer shell. Does that make sense? All right. So that's kind of cool. So again, it gives you another way of making certain that your electron configuration is correct. Now, I mentioned previously, if we look at the periodic table and we consider the shape of it, we see something quite interesting. This block over here on the periodic table is 2 groups wide. This block over on the far left of the periodic table is 6 groups wide. This bit in the middle of the periodic table here that sits lower than the 2 end bits, where the B group elements are, that is 10 groups wide. And then this guy at the bottom here, you guessed it, 14 groups wide. So 2, 6, 10, and 14 correspond to the maximum number of electrons in an S subshell, a P subshell, a D subshell, and why did I write 14? An F subshell. So we can think of the periodic table as being divided into blocks or areas. The first 2 columns on the far left we call the S block. The 6 columns on the far right we call the P block. 10 columns in the middle of the periodic table we call the D block, and the 2 rows each containing 14 columns below the periodic table we call the F block. And what we will observe is that we can actually count off an electron configuration using the periodic table. So for example, it goes 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2, 3p1, 3p2, 3p4, 3p5, 3p5, 3p6, and so on. So that's kind of cool. And what's really nice is we can always figure out where our electron configuration is meant to end. So this is row 3 in the P block. So this would be 3p1, 3p2, 3p3, 3p4, 3p5. So whatever element is there, its electron configuration should end 3p5. And that can be really helpful for making certain that our electron configuration is correct. And if you really want to, you can count off the electron configuration like that. Most folks find it easier to use an Aufbau diagram. So, as I was saying, if you want to, you can use the periodic table instead of the Aufbau diagram in order to remember the order that the subshells are filled in. So you could start 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2, 3p1, 3p2, 3p4, 3p5, 3p6, 4s1, 4s2, 3d1, all the way through 3d10, back to 4p, 4p1, and so on. And if you want, you can use this method. Like I said, most folks find the Aufbau diagram is a little easier. We can define a valence electron as an electron in the outermost shell. So it's important to realize that inner shell electrons are not involved in chemical reactivity or determining the properties of an element because they are buried inside this layer of the outermost shell. The inner shell electrons are called the core electrons, and you'll find that they're always in the arrangement of a noble gas, and they're not at all going to be involved in determining chemical properties. So for example, if we look at the electron configuration of sodium, there are 10 core electrons that are in the arrangement found in neon, and then there is 1 valence electron. That's why we write the abbreviated electron configuration as neon in square brackets followed by 3s1. So the abbreviated electron configuration does help us understand very clearly what are the valence electrons and what are the core electrons, but an even more elegant system was developed by an American chemist called G.N. Lewis. And he uses a pictorial system to illustrate the number of valence electrons a particular element has. And it's really, really simple. All we do is to write the Lewis symbol of an element is we write the element's symbol and then we place dots equal to the number of valence electrons around the symbol. So for nitrogen, it has 5 valence electrons. So what we do is we place 1 at each of the 4 compass points. And it doesn't matter where you begin. And then at one of the compass points, we double up. And so that's it. It's really, really simple. And the important thing to remember is that for a representative element, one of those that's in the A groups of the periodic table, the number of valence electrons, or the number of dots that you will add to generate the Lewis symbol, is always equal to the group number. And that's it. And yeah, that's a real simple way of showing the number of valence electrons that an element has. So we're going to go ahead and write the electron configuration of an atom that has 20 electrons. And we're going to use the periodic table to help us guide how to do this. So the element that has 20 electrons is calcium. It's in row 1, 2, 3, 4 of the periodic table. And it's in the S region of the periodic table. So because it's in the second column of the S region, what I know is that the electron configuration of calcium will end 4s2. So now I'm going to write out the Aufbau diagram, and I'm going to begin by writing 1s all the way down to 7s. And then for the second column, I'm going to start writing 2p all the way down to 7p. And then for the third column, I'm going to write 3d all the way down to 7d. And then for the fourth column, I'm going to write 4f all the way down to 7f. And then I'm going to put in my arrows showing the order of subshell filling. And I'm going to stop at 4s because I know I don't need to go any further than 4s. And so now I can write out the electron configuration: 1s2, 2s2, 2p6. Just following along these arrows, when I get to the end of one arrow, I go to the beginning of the next. 2p6 gets me up to 10 electrons. I'm going to go 3s2, 3p6. That gets me another 8 electrons, so I'm up to 18 electrons, up to the 3s. And then up to 3p6. And then now finally I move on to 4s2, and that gets me to 20 electrons. So I'm just following down the arrows. When I get to the end of one arrow, I go to the beginning of the next one, and I just keep filling up until I get to where I'm meant to. And if I count this up, 2 plus 2 gives me 4, plus 6 gives me 10, plus another 2 gives me 12, plus 6 gives me 18, plus another 2 gives me 20, which is what I wanted. And I know it's correct because it ends 4s2. Now, if I want to write the abbreviated electron configuration, I can just write the symbol of the previous noble gas in parentheses. That counts for 18 electrons, and then I just write the valence electrons outside. So there we have the full electron configuration of calcium and also the abbreviated electron configuration, and we were using the periodic table along with the Aufbau diagram to make sure that we have everything set up correctly. Okay, so that concludes the section on the arrangement of electrons in atoms.